what we're going to do here is we're going to look at a few examples of how we could evaluate an infinite limit on a rational function. Does everybody know what I mean by a rational function?
Yeah, sure.
Rational comes from the word ratio. Ratio is a fraction. So a rational function is a function that is a fraction, a polynomial divided by a polynomial. They come from the same root, but it doesn't have anything to do with like being a rational person, at least that use of it. Although that was the original use of it, kind of. Because, well, we'll get into it later. Irrational numbers, never mind. We don't need to talk about it now. I'd really like to, but we've got more important things to talk about. Okay, so let's look at what would happen with something like this. It's just a really poorly written problem. Let's just say that x is going to infinity instead of n is going to infinity, since that's really what we want to do here. So as x approaches infinity, well, first of all, we can't plug infinity in. Infinity is not a number. And so what we need to understand is we can't use direct substitution with infinite limits. Now, there are going to be some times when we can plug infinity in and we can get answers, but those answers are always going to be in terms of infinity. Some things that we don't know are like what infinity minus infinity is, or infinity divided by infinity, because we don't know how big the infinity is. Because one number can be increasing faster than another number, and so infinity divided by infinity could be different. So what we're going to do to evaluate this is we're going to use algebraic manipulation like we've done with other types of them. Most of the limits that we've used algebraic manipulation with have been where we have a hole in a graph. And so we can cancel out a numerator with a denominator, and all of a sudden we don't have 0 divided by 0, but we have something else. We're going to do the same type of thing here, but it's a different trick. The trick here is what I'm going to do is in the numerator and the denominator, I'm going to divide by x to the highest degree. And just as a rule, I like to use the highest degree in the denominator. It doesn't really matter if you do the highest degree overall or the highest in the denominator, highest in the numerator. Different things are going to happen, but I like to use the highest in the denominator. So what I'm going to do is I'm going to divide the numerator and the denominator by x cubed. Okay, so what I'm really doing is multiplying each of those by 1 over x cubed. And so this is going to change the look of it, but since we're multiplying the numerator and the denominator by the same thing, then it's going to look different. Now, one thing I want you to notice here is what I'm really doing is multiplying by 0. Anybody tell me why I'm actually multiplying by 0 here?
Because it's so close to 0.
What would be close to 0?
1 over infinity.
Yeah. This is going to end up being 1 over infinity. So what I'm doing is I'm multiplying by 0. But since x is not actually equal to infinity, it's not actually infinite, it's just approaching that, then we don't have to worry about it. Okay? It would be bad, though, if I said, okay, well, I'm going to multiply by 1 over x cubed here and 1 over x squared here, because even though they would both approach 0, they approach 0 at different rates, and so they're different zeros. That's just kind of deep, but yes.
Is that number 3?
No, that's analysis. So, what is 3x cubed divided by x cubed?
3.
All right, one thing to keep in mind, we leave our limit on as long as we don't substitute it in. So we have the limit as x approaches infinity of 3 plus 4x squared divided by x cubed is going to be 4 over x minus 5x divided by x cubed is 5 over x squared, and then 10 divided by x cubed is 10 over x cubed. Okay, and then in the bottom we're going to have 6x cubed divided by x cubed is 6 minus 5x divided by x cubed is 5 over x squared. Okay, now, where we couldn't just plug infinity in for x here because we would have infinity plus infinity minus infinity plus 10 over infinity minus infinity, we have a bunch of infinities that we don't know how to evaluate. Now we can plug infinity in. And why can we plug it in now?
Zero.
Yeah, they're gonna make zeros. We know what 0 plus 0 is, where we don't know what infinity plus infinity is. Although it's going to be infinity. Okay, let me say that a different way. We know what 0 minus 0 is, but we don't know what infinity minus infinity is. All right, so when we plug infinity in, if it's going to be in the bottom of a fraction, that's just going to make that fraction approach 0. So that's going to approach 0, that's going to approach 0, that's going to approach 0, and that's going to approach 0. So once we plug infinity in, first of all, we can drop our limit now. And we have 3 plus 0 minus 0 plus 0, which is 3, over 6 minus 0, which is 6, and that's going to be 1/2. Now, the shortcut for this, if you guys remember, when the degree is the same on top as the bottom, what can you do? Divide the leading coefficients, right? And what happens, these leading coefficients are the only ones where we don't have an x in the denominator. So we can just divide those leading coefficients and we get to this step right off the bat. Okay, so this is what's happening. This is why you can divide those leading coefficients. So you can just use that shortcut. So when the degrees are the same, divide the leading coefficients. Here the degrees are not the same. So let's look at what's going to happen here. I think you guys know the trick or the rule. First of all, that should be an x approaching infinity again. But let's just work through it and gain a deeper understanding of this. The degree on the bottom is 3. So I'm going to divide by x cubed, or multiply by 1 over x cubed on the top and bottom. And so when we do that, we're going to get the limit as x approaches infinity of... What's 4x squared over x cubed? 4 over x minus 5x over x cubed, which would be minus 5 over x squared. And then plus 10 over x cubed is 10 over x cubed. And then in the denominator, we have 6x cubed over x cubed is 6 minus 5 over x squared. Okay, so this time, when we plug infinity in, we get all 3 terms that go to 0 in the numerator, and 1 term that goes to 0 in the denominator. And so what we get is 0 over 6, which is 0. So the rule here is when the degree on the top is smaller than the degree on the bottom, then what we're going to end up with is all the terms in the numerator going to 0, and so it's going to approach 0. That's the same as when we draw a function like this, it's going to have a horizontal asymptote at the x-axis. Okay, the last case, we have degree on top is bigger than the degree on the bottom. So again, we're going to multiply by 1 over x squared this time. Like I said, I always like to just make it simple and divide by the degree on the bottom. I could do over x cubed, but then something kind of funny happens in the denominator that we have to think more than we really like to think sometimes. You guys like to avoid thinking when possible, right?
Of course.
So we've got the limit as x approaches infinity. Sorry, that should be an x again. So in the numerator we have 3x plus 4 minus 5 over x plus 10 over x squared. And in the denominator we end up with 5 minus 1 over x squared. And the reason I like to divide by the degree in the denominator is because then we always have a finite number in the denominator, and so we really have to just worry about what's going on in the numerator. If we end up with 0 in the denominator or infinity in the denominator, it makes us think a little bit more. All right, so we've got terms that go to 0 here. But we have one term that doesn't go to 0 and also is not finite. We've got that 3x there, right? Now, I've said already that we can't just plug infinity in for x. But let's think about what's going to happen here when this x increases without bound. Okay, so 3 times infinity is infinity, plus 4, still infinite, right? We're not really changing that. So we have an infinite number, a number increasing without bound on top over a finite number. What's that going to be? That's going to be infinite. Now, I'll tell you right now, as far as approximating areas under curves, we shouldn't get something that happened, or we shouldn't get anything like this unless we're finding an area that has an asymptote involved in it. But even in that case, things are a little bit tricky, and we'll deal with those when we get there. For now, we're going to be dealing with simpler functions anyway, so we don't need to worry about that. All right, so when the degree on top is bigger than the degree on the bottom, what's going to happen? It's going to be infinite. Now, we have to be careful. It could be positive infinity, like it is here, but it could also be negative infinity. If this leading term here was negative, or if this 5 here was negative, then this would be a negative infinity. Why would this 5 being negative make this a negative infinity? Yeah, exactly. We would be dividing our positive infinity on the top by a negative infinity on the bottom. All right, so even though we're dealing with this idea of infinity, the rules of positives and negatives still apply with multiplying and dividing.